Okay, welcome to the second part of lecture 13 of the Inverse Problems course. And now let's delve deeper into the topic of wavelets. Or I try to explain the basic ideas about them. So in MATLAB, I'm using the Wavelet toolbox of MATLAB. And let me first show you some stuff in dimension 1, how the wavelets work in dimension 1. And let's there are some, there should be some ready-made signals in MATLAB already. So let's take something like some discontinuities.
Is this a special package you downloaded, or?
Sorry?
Is this a special package or something?
Yeah, it's a MATLAB's Wavelet toolbox that needs to be for this one. But I think let's start with the step signal. So here what we see is, first of all, here is an original signal in red that just has one jump here. And now here it's possible to change which wavelet to use. So let's use HAR, because that's what we use now in our work, and I'll push analyze. So now actually we see that there are consecutive approximations of this function we see here. This is with kind of bigger steps, and this is twice smaller, twice smaller, twice smaller, and then we don't need smaller than that. Something like that happens. Maybe this is not such a great example. Let's take something.
Sorry, that one was not using soft threshold.
So far, what I'm showing you right now is just the wavelet decomposition of signals. There is no thresholding at all. I'm just showing you all the wavelet. Let me again go to this HAR wavelet. Let's do still maybe a couple of more steps and analyze. So I'm trying to give you an idea how wavelets work. So the red here, again, red is the original signal, which is first this lower frequency sign and then this higher frequency sign. And now it has been divided into many parts. We could start from the bottom. So this is the finest scale part, which shows what happens if you take the finest scale coefficients, which now correspond to step functions that have in the nearby pixels, well, not but sampling points, they have value -1 and +1 with some constant. Otherwise, they are all zeros, but they have -1 and +1 in consecutive pixels. So, and then in the next part, this describes the next biggest details that are actually 4 sampling points wide, like -1, -1, +1, +1. That kind of building blocks. And yep.
So all levels are like a sum of all the coefficients by all the wavelets on that precision level.
Yes, so what we see here, the red curve equals the sum of all of these other signals we see here. So if we sum up all the functions we see here, all these 8 functions we see here, if we sum them, we will get the original signal back. That's the first observation maybe. So it's really an orthonormal decomposition of our red function into completely independent orthogonal parts. And the bottom guy here collects the smallest details. This one twice bigger, this one twice bigger, twice. So here you start already to see that here, so in this level, the smallest detail has kind of this size. It has this kind of shape. And in the next level, it's 2 times smaller. So we have things like this. No, I mean, my explanation is so poor, sorry. And then we go twice smaller details, and smaller, and smaller. Yes?
Yeah, so it seems like there's actually not so many, not so many zero coefficients.
That's right.
Yeah.
Almost no zero coefficient. I think there are no.
That we happy like putting them to zero if they're not small. Is the point only packing, or is it like maybe at some point the noise reduction that
Those are both very good points. With wavelets, the strength of wavelets, they have many strengths. One is noise reduction, because often the noise will appear only on the smallest scales. And one thing is that now I'm using the hard wavelet, which is it's nice for teaching purposes because it's very clear. It's piecewise constant. It's easy to consider. But there are many other wavelets. For example, this Dobeshi wavelet series, we can take higher Dobeshi series, and there now you see that at the smallest details we have pretty much now zero coefficients. Here, where there is this abrupt change, a discontinuity here, that will have an effect. You see, it has an effect at all scales, even the smallest ones. So to describe discontinuities, we need all wavelets down to the smallest detail. But as you see, to the left and to the right of the discontinuity, on the smallest scale, we have just zeros. This is because of so-called vanishing moments. It depends on what is our basic building block in the wavelet expansion. It has always 2 basic building blocks, the mother wavelet and the scaling function. And if the mother wavelet has some vanishing moments, it means that we don't. If our signal is smooth enough, then we don't need those wavelets at all. I mean, for Haar is piecewise constant. So there, if our signal has long constant parts, if our
So this sort of like a Fourier transform, except we're using like shorter bits of wavelet, these like sine waves.
yes, this is very much related to Fourier transform, but it's different because with wavelets we can work with with the Fourier transform we can only localize either in frequency or on the function domain. So because the sines they are non-zero pretty much everywhere except for the isolated 0 points. And wavelets provide a possibility of being not completely compactly supported, but almost compactly supported in both frequency and time domain or the signal domain. Yes.
But let's say if you like used sine wavelet, so that you could use.
Not exactly, because the wavelets decay at infinity. They can even be compactly supported, or they go to zero very fast outside some interval.
Yeah.
It's idea that they are localized functions. Their idea is to be localized, and sine is not localized.
What means what does localized?
Outside a finite interval, the function is either completely zero or very close to zero.
You
Yeah.
just take like a bit of sine wave.
Yeah, that's what.
Like it's 0 and then you have like 1.
That would give that's very much related to so-called windowed Fourier transform, which is a useful tool as well. But the wavelets provide an even more clever tiling of the time frequency space.
But the point was only that if you take the mother wave
Yes.
to be the shape of sine, and you just make those sine x, sine 2x, sine 3x, because it just seems that it would be a good fit, good wavelet, good mother wavelet to present that kind of.
In a way, yes. However, the mother wavelet has to satisfy some assumptions, so that this multi-resolution analysis has the good properties, the orthonormality, and all the properties we want. So not any function can be a mother wavelet. There are some assumptions, and just truncated piece of sines, I don't think that works.
Yeah, they wouldn't be like.
Yeah, there will be problems with several assumptions. So there are only some. So that's why, for example, in this wavelet toolbox, there are these. So there is this collection of wavelet types. There are still even more, but these are some of the most important ones. So we can easily use them here. And maybe if I still. Oh, sorry, no. Take the step. So for the step signal, again we see that only the discontinuity is seen in these lower levels. But here we see that already at this point everything is zero outside. And even I think with the hard wavelet, it's mostly zero here. So hard wavelet, when it needs to represent a constant function, like in this part, we don't need them at all, because the inner product with the hard wavelet has equally positive amount and negative amount, so it will give a zero coefficient with a constant. But then even if we have don't we have any? Well, it doesn't have exactly the example I would like, but anyway, so here if we use hard wavelet for this kind of situation, because it's not constant, our signal is not constant anywhere, so we will need hard wavelets down to the smallest detail. We need them all. But if we take a more smooth mother wavelet, then it happens that it's not completely zero yet, but it's getting close. So we see that here, near to discontinuity of the derivative, we need some of these small ones, and also in the beginning and end of the signal. But here, we almost don't need them anymore, because the signal is smooth enough at that point. Maybe if we go even higher, then you see that now actually we have pretty much zeros here. So this is related to the mother wavelet choice. How smooth is it? How many vanishing moments does it have? So then how do we need them to represent a signal in the area where it has some smoothness? Yes. I had the honor and pleasure once to ask them directly from Ingrid Dobeshi when she gave a talk in the US in one seminar, and she said that yes, it depends on what kind of signals are you trying to represent. You need to know about the signal. What is the smoothness of the signal? What kind of properties does it have? Discontinuities. So then yes, when you know more about the signal, then you can choose the mother wavelet. For example, if you know your signal is piecewise linear, for example, then the hard wavelet is not so good, because even for the linear trends you will need the even smallest ones. But I think for linear signals already the Dobeshi 2 wavelet has the vanishing moment property is such that for linear ones we don't need the small ones anymore. We need only the bigger ones. So there are things like this to think about what kind of data you want to represent. Yes. Okay, so I really don't know how clear this thing might be at this moment, but the basic idea anyway is to, so here we see, when I take the step signal, just to show you how the mother wavelets look like. So in this case, the mother wavelet looks like this. It's rather strange because it's a result of mathematical theory, Dobeshi's breakthrough work, where she wanted to have compactly supported mother wavelets that will yield a good multi-resolution analysis with all the desired properties. And she could find a method to construct compactly supported mother wavelets with the properties, but then the thing is they are a bit unsymmetric and they look like that, which is maybe, depending on the viewer, it may be a bit strange. So that's Dobeshi 2, and if we go forward in the sequence, we get these further functions. They are quite intriguing, and there is a lot of information about the smoothness properties of these. The higher you go, the more smoothness you have, some more continuous derivatives you have. And there are other families as well existing. But now, this is to give you an idea that for one-dimensional signals, the wavelet transform will divide the signal into independent parts containing details of a certain size. At the bottom, the smallest details, and the details always have the same shape. You take the same mother wavelet, and for the next level, you squeeze it by a factor of 2. And for the next level, again, you squeeze it by a factor of 2, and so on. Always you squeeze it by a factor of 2. They will be orthonormal by the construction, and then you can represent these smaller and smaller details using the same basic shape. Okay, so if it's okay, I will move to two-dimensional signals. Any questions about the 1D? Okay, if not, let's look at couple of examples with two-dimensional signals. So we have here the two-dimensional one. So I'll take the wavelet 2D, and let's take, for example, the fingerprint image, because that's the fingerprint image represents one big breakthrough with wavelets. I think it was in the 90s when FBI needed to compress fingerprint images in their digital repository of images, and they were looking for a good enough compression method so that when decompressed, the fingerprint information would be still good. So wavelets won that competition because by this kind of thresholding wavelet coefficients, it turns out that it gives a very you can put a lot of wavelet coefficients to 0 and still retaining the usefulness of the image. It's a really good compression method. So what happens here? Let's use the hard wavelet like we did in the tomography computation, and let's first just do one level. We'll do the analysis. You remember this kind of, oh, maybe the fingerprint is not such a good, let's take another image. Maybe it's more natural to see. I think this is maybe the Barbara image. Okay, so here you see these 4 images I showed you with the walnut, and what's happening here is okay, I think the resolution is doing some tricks to me here. Because I should be able to, well, Anyway, so what happens here is like you remember in the one-dimensional signal there was at the top there was the low pass part, and then did I mention that? Maybe I didn't. Let me mention it again. So if you go back to the 1D signals, so the blue one is the low pass part, and then the green ones are the successive detail levels. Smallest detail, double that size, double, 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 and then this is the low pass filter. Because how this transform goes in practice, we start by computing the details, so this one, and then the algorithm, so if we do this only for one level, then we only have the low pass part and details. But if we want, we can divide the low pass part further. So if I take, instead of one, I take two levels. Then this one is the same than before, but we added this one. So we actually further divided the previous low pass part into details and low pass. And we can continue this to do more and more of these. And always the blue one is the remaining low pass part after checking all of the details in different levels. And we can do this many times, and you see that now the blue one is really, really low pass part, just like this, and then we go with the details. So there's that kind of thinking in the wavelet transform. You do a desired number of detail levels, and what remains is the low pass part is what remains after taking out all those details. So in 2D we can do the same thing, but now something changes because we go from 1D to 2D. And now what changes is, now if I take only one level, is now we have four things here. Previously in the 1D image we had the low pass part and we had a detail part. So two things. Here we have four things. That's because we do the low pass filter and detail horizontally and vertically in the 2D case. So the 2D wavelet transform in this so-called tensor product way is done that we do the same thing we did in 1D to the rows and columns of our pixel image. But for each row and column, we can do one of two things, the low pass or the detail. So that's why 4. This image means that for every row and column, we have made the low pass. Here, this is this is called the vertical details. So here we did the details horizontally and low pass vertically. Here we do the details vertically and low pass horizontally. And here we do details both horizontally and vertically. That's why we get 4 parts in the wavelet transform.
So is this related to the orthonormality if you have to apply the horizontal and vertical parts?
I think because of the orthonormality, you can do that. You could do the wavelet transform only horizontally. Then you would get 2 images that are kind of elongated. But this is usually a more useful way to do it both ways. But yeah, because of the orthonormality, that's something you can do. Because the tensor products of the building blocks, 1D building blocks, when you do the tensor product in 2 dimensions, they remain orthonormal because you can carry this 1D orthonormality. I wonder why can't I take... Anyway, so then we can take 2 steps, meaning that we further transform this low pass part here. So these details, these 3 detail things remain the same, but the low pass part we again divide like this. And we can keep on doing this for many times. If our image has size 2 to the n times 2 to the n, we can do this n times, so long as the low pass part is only 1 pixel. Then we have to stop. But so we can keep on dividing it like this. And in this picture you see the coefficients of building blocks of different sizes for the image. And again, all this information is completely orthonormal. Now again, at this point I don't know if this makes any sense. Any questions maybe, or?
So what do the 2D wavelets look like? Since in 1D we have those like, you know, bits of wave, and what do the 2D ones look like?
I think so. It's kind of a tensor product thing. So you take it. You take a function of two variables x and y, and then when you have this one-dimensional wavelet shape, which is just a function of x, then your wavelet as a function of x and y is the product between 1D wavelet at x times 1D wavelet at y. That's how they look. And in this tensor product thing, you only multiply together the same scale functions. So that's why you get kind of square-shaped things. Again, I don't know if this explanation makes any sense, but in the exercises you have the pleasure and happiness to compute the 1D transform and see how it works for 1D signals, and then really what happens in this 2D case. The same thing is just done horizontally and vertically, resulting in this kind of development of the image.
Can you omit some of the levels? For example, what if you omit the most left, most corner one, the low pass?
I would love to do that, but somehow I think it's a resolution thing. In the Wavelet toolbox, it should be possible to click one of these images and then either show that part or reconstruct only that one. I'm sorry, I seem to be unable to do this. I don't know what the problem is. It just doesn't work. You need to try it by yourself, how that works. Maybe the basic message here is that it is possible to go, maybe if I do the compression, let's see. At least here we see when we are, so here I'm thresholding the wavelet coefficients according to size. So here's a slider we can compress. So now I'm not compressing at all. So here we can set a threshold. Something like, well, maybe if I just move this one. So we have a threshold to putting things to 0. This will show how much of the image quality we still have in an L2 sense. And this tells how many, what's the percentage we put to 0 of the coefficients. So here, now you see already quite a difference in the image quality as well. I think I went a bit over of the so you can see there's also some noise in the image. Here you see that the noise is gone, although it's a little bit blocky. And here you can see these little small details of the checkerboard type from the smallest details. And then here you can see that in the L2 sense, most of the quality of the image has been retained, although by human eye we can see some difference. But we have already put to zero almost 90% of the coefficient. So this is somehow the compression power of wavelets. And I think we could actually use also some other wavelet like Dobeshi, a bit higher Dobeshi, for example. And then if we compress, I think we might be able to get something better. So here, well, we see some degradation of the image, but also the noise is gone pretty much. We see a little bit of this wavelety look here, but also we see that we have again put to zeros 90% even more, and at least in the L2 norm we are retaining the image quality almost completely. So this is the compression power of wavelets, and that's, I think, somehow why it's interesting to try it for the sparsity promoting reconstruction as well. So it seems that at least 1/4 of the coefficients we can just safely just put to zero and we will retain 100%. I think that's because of vanishing moments. Wherever there is some smooth area in the image, we don't need the smallest wavelets. The coefficients are zero.
What's the image look like now? Compressing.
So now we are not throwing too much away. It's pretty much the same. But I encourage you to try out this demonstration, to get your own hands onto it, and also you will be able to try out the different parts of these and make reconstructions. Yes.
Yeah, I remember this picture has actually quite a lot of detail, like
Yes.
stripes.
Yes.
So basically, we tried this at the same course that I talked about. And I like some pictures which seem to be quite detailed, but actually have more of those constant things. And we used our wavelet, and we could like throw away maybe 97%
Yes.
information, and still my eye didn't notice it.
Yeah, it really, and this is back to the nature of the mother wavelet you use. If you know your image has large parts of constant or kind of smooth parts, then if you take the mother wavelet that has a suitable number of vanishing moments, so that in the smooth part we just don't need the small detail wavelets at all, then you will be able to compress a lot, really, without any visible problems. Actually, I also promised to say something about the back projection. I'll do that now so that it doesn't remain undone. So I think for the wavelet part, you need to get into it and study it and try out these methods. I hope this gave at least some understanding. But now anyway, so if I clear all here, and let me just load in the data. Okay, maybe I have to change folder. Let's just stop the iteration. So now the A matrix. The A matrix we take that, of course, it will map a pixel image into a sinogram. That's what A is doing. Now, what is A transpose doing? This is very important, actually. So let's first let me first take a temporary image. Let's take, for example, the phantom image, and let me. This is the size of M. Let me compute the data from our phantom image, which would be A times temporary image dropped as a vertical vector, like this. And now if I just show what happens when I reshape the remaining histogram into.
Is this your own function also?
Reshape is from MATLAB.
Okay.
It's just, yeah. Reshape, oh, sorry, reshape. Sorry, I have to close the images. Let's make a new figure. So sorry, the dimensions are wrong, but anyway, so I just took the Shep-Logan phantom and computed the sinogram of it. That's what we do usually. So this is multiplication by matrix A. So I take this phantom and multiply it by matrix A. After dropping to vertical vector, I get another vertical vector, which I reshape to the shape of the sinogram. Now, the transpose of A multiplies a vector of the size of the sinogram, and the result will be a pixel image of size n by n. Let's see what it does, and let me make another. Let's make a dummy sinogram with only zeros in it. So now we have a zero sinogram instead of the sinogram of the walnut. And let me add just one element there, just somewhere. I will just put to 1. So now we have a strange sinogram. Let me put axis equal. So here I have a sinogram with just 1 point equal to 1. Let me back project this, meaning I will multiply. So back projection, I say that is A transpose times this weird sinogram I made. Back projection. So let's see what is back projection. Back projection. And let's make axis equal.
If you reshape it to drop it as a vector.
Oh, yes. Something is missing, maybe. Oh, this should be, of course, n by n. Why? What is this? What is this? Let's try another one while you think. Let's do another one. So we do. But that's in the image space, in the space of f, n by n images. The sinogram is in the other. So I took another one. So this domain, image domain here is the domain of f. It's our imaging domain where our object is. What is this? I back project just one element from the sinogram. I have a sinogram full of zeros except for one element, which is 1. And we see this in the image domain when I back project. Any ideas? What might be going on? Yes?
It's kind of, if you put X-rays just through this in the same direction, it shows the point, but in any other direction it's 0 because it's so thin.
And this is really, yeah, this is one of the X-rays in our measurement.
So it's kind of some object which is so thin that it's 0 in every other direction, except 1.
Yeah, this is actually showing the path of one of our X-rays. Yeah, so yeah, and this is what the back projection is doing. It takes a sinogram and it sends whatever is in the sinogram, it sends it back to the image. Let me show you another example. So that was just one ray because I put just one value 1 in the sinogram. Let me do another trick. Let's do again a 0 sinogram, but now I will take one column there. And what is a column in the sinogram? Anyone? Yes.
It's like the values to one direction of those.
Exactly.
Those,
yes.
X-rays.
Yes.
Like
So it's
values.
So it's one X-ray image, but it's 2D tomography, so the image is 1D. But this is one projection direction. This is the projection image, one column. So now I'm putting into one column, I will put just random values. Otherwise it's 0, but I will put just random values there. So now our sinogram has otherwise 0 projection images, but one projection image has random values. Let me apply the back projection. Back projection, and let's see how it looks like. So you see here we have completely zeros in this little triangle here. And here in the other triangle, we have just zeros, because that's outside the fan beam. Inside the fan beam, the back projection is sending the image we have on the detector, it's sending it back along the rays. That's why it's called back projection. That's the transpose of the tomography matrix. It's an extremely important operator in every reconstruction method we use in the course. It contains the transpose of A. And every time you multiply by the transpose of A, you should think that this is what you're doing. You're sending the sinogram at that point, maybe for the iterate. You have some iterate picture, Fn, going on in your iteration. So it's kind of the current best guess what is the image. And usually you take the X-ray image of that guy, you take the X-ray image of your iterate, you subtract, so this is the virtual X-ray image of the iterate, just simulated by the matrix. This is the real data, G. So you subtract, so you look at the difference, the error in the data between the real data and your simulated data for the iterate. And then you back project the residual. You back project the difference into the image space. That's what's going on here. It's good to have an understanding what is really going on when you do it. So that's something to think about. Our time is up, so please think about the back projection matrix. Try out the Wavelet toolbox a little bit, and also work on the exercises containing wavelets. Okay, thank you.